theorem 4.1.7, the supersystem principle for non-homogeneous equations. So let y sub p, y sub 1, y sub p sub k all the way to y sub p sub k be k particular solutions of the non-homogeneous linear nth order differential equation. 7. On an interval I corresponding in turn to k, distinct functions g sub 1, g sub 2, g sub k. That is, suppose y sub p sub 1 denotes a particular solution of the corresponding differential equation, where I equals 1, 2, all the way to k. Then y sub p is equal to y sub p sub 1 plus y sub p sub 2 plus all the way up to y sub p sub k. All those are functions of x. Is a particular solution of, and then we have that differential equation is equal to g sub 1 of x plus g sub 2 of x plus all the way up to g sub k of x. So basically what this is saying is if we have a bunch of different functions, so like a g sub 1 of x and a g sub 2 of x, so we have some different functions to the right, then we can take particular solutions of each, like the g sub 1 of x, so the particular solution of g sub 1 of x would be, y sub p sub 1 of x, plus the g sub 2 of x, that would be a solution. And so if we have a bunch of, particular solutions that represents, solutions to a combination of a bunch of functions in our differential equation, then, we're able to write our particular solution as the sum of all those particular solutions. All right, so let's just kind of talk about what that means, and I'll give you an example. And it's probably easier to see through the example than me just explaining through everything. And so the proof of this superposition principle. Now, we're going to prove case where k equals 2. So we're only going up to, two different distinct functions. All right, let L be the differential operator in 8. So let's just say let L be the differential operator. So instead of saying, all of this, we can say L of y equals g sub 1 of x. So instead of having to write all that, because we know that's a linear nth order differential equation, we're using L to show that that's a linear and then differential equation on the left-hand side. And we're going to let y sub p sub 1 of x and y sub p sub 2 of x be particular solutions of the non-homogeneous equations, L sub 1. So we have two solutions. We have L sub y equals g of x, or we'll say g sub 1 of x, and L of y. So again, our differential equation is equal to g sub 2 of x. And we're told that y sub 1 of x, or y sub p sub 1, is a solution to g sub 1 of x, and y sub p sub 2 is a solution to g sub 2 of x. If we define our particular solution as y sub p of x is equal to y sub p sub 1 plus y sub p sub 2, both of those of x. I should write that too. I wanted to show that y sub p is a particular solution of Ly is equal to g sub 1 of x plus g sub 2 of x. The result is going to follow our rules for linearity. So if we have L sub yp, so we're plugging in our particular solution into our differential equation, we're going to have our differential equation be made up of y sub p of 1 of x plus y sub p of 2 of x. That's just going to be our linear differential equation as y sub p of 1 of x plus, I'm going to put too many parentheses, plus our differential equation with y sub p sub 2 of x, which is just going to equal g sub 1 of x plus g sub 2 of x. So basically all this proof is saying is that if we know that these two are solutions to our linear differential equations, we put it into our linear differential equations. When we're working it out, it's going to be broken up into basically our differential equation of y sub p of 1 and our linear equation of y sub p of 2. And when it breaks up that way, g sub 1 of x is going to correspond to y sub p of 1, the linear differential equation of y sub p of 1 of x, and then the linear equation of y sub p sub 2 of x is going to correspond to g sub 2 of x. Yeah, the proof would be easier if we actually saw some functions in there, but you didn't have enough room right here to write out a proof kind of like I did at the beginning for the superposition principle with the homogeneous equations. Alright, so let's look at example 9. Verify that y sub p sub 1 is equal to 3e to the 2x and y sub p sub 2 is equal to x squared plus 3x are respectively particular solutions of these two differential equations. So let's go ahead and take our derivatives of y sub p sub 1. That's just going to be 6e to the 2x. And our second derivative of p sub 1, which is going to be 12e to the 2x. And then let's plug it in to our differential equation and make sure that this is a particular solution. So we're going to go ahead and plug this in to our differential equation. So y double prime is going to be 12e to the 2x minus 6 times 6e to the 2x plus 5 times 3e to the 2x, and that should equal negative 9e to the 2x. Alright, so we get 12e to the 2x, 6 times 6 is minus 36e to the 2x, 5 times 3 so plus 15e to the 2x. And when we do the math, 12, 15, it's going to give us 27. The difference of 27 and 36 is minus 9, so we do get negative 9e to the 2x. So that is a solution. Alright, let's check the other one. Alright, so y prime p sub 2 is going to be 2x plus 3. Whoa, that's this first derivative, not the second derivative. And then our second derivative is going to be just 2. Alright, let's go ahead and plug that in. So we have 2 minus 6 times 2x plus 3. Now, 3's are really not working. Alright, plus 5y. Plus 5y. 5 times x squared plus 3x. And that's supposed to equal 5x squared plus 3x minus 16. Alright, so I get 2 minus 12x plus, yeah, it's 6. Plus 8, minus 18. Plus 5x squared, 5 times 3. So plus 15x equals, and so let's just go ahead and combine those. We're going to be left with 5x squared. Plus 3x minus 16. Alright, so yes, they turn out to both be solutions to this differential equation. And notice that the differential equation on the left-hand side is the same. Alright, so since they both are equal to the same linear differential equation, this is g1 of x, that's g2 of x. If we combine those two, like say here, so 5x squared minus 9e to the x, so 5x squared plus 3x minus, so we combine g sub 1 and g sub 2, and that's equal to the same differential equation that we saw on the left-hand side, then we already know what the solution would be to that first one. So the solution for, trying to get a one that you can see. So our solution to the first one, we'll call this, solution to I, and then we'll call that 2I. The solution to I is just going to be y sub p is equal to just the linear combination of the two solutions. So 3e to the 2x plus x squared plus 3x. So there's our solution. Right? Because this could be broken up as, that's g of x, that's g of x, so they match the same. Minus 90 to 2x, minus 90 to 2x. Now, what about number 2? Well, number 2 can be written, let me change the color again. Alright, number 2, y double prime minus 6y prime plus 5y. So it's the same differential equation, but it's set equal to negative 10x squared minus 6x plus 32 plus e to the 2x. Alright, so can we rewrite this? Yes, we can. Alright, so what we can do is we can go ahead and pull out a negative 1/2. Or sorry, we can pull out a negative 2. If we pull out a negative 2, we're going to get 5x squared plus 3x minus 16. All right, so we have negative 2 times, and we say, this is y sub p of 2. Plus, all right, we need a 9 in there, so if we pull it out, it's minus 9. We want it set equal to 3, let's see, we want it set equal to minus 9 e to the 2x. So we're going to have to pull out a minus 1/9 so that we can get a 9. Oh, I kind of working on a different line. So minus 1/9. That way we can put a 9 in there, 9 e to the 2x, have a negative in there because, actually we'll just keep that positive because we want a negative on the inside. Alright, so if we do that, then we're still going to have, so we have minus, and then we are left with, could have just kept it on the outside, so minus 1/9, actually plus 1/9, e y sub p of 1. Now we can go ahead and plug in our solutions, which is going to be negative 2, so our y sub p is going to be equal to negative 2. Our yp of 2 is x squared plus 3x plus 1/9. Our yp of 1 is 3e to the 2x. So we're left with negative 2x squared, let me zoom in so I can have some more room, negative 2x squared minus 6x plus 1/3 e to the 2x is our solution. I'll box up all the solutions and we're finished.